you want to see the moon and the stars at the same time, what you need is a long exposure photograph. And here's one that I and my colleagues took down in Cornwall in the southwest of the UK. And you can see that the moon is elongated in shape. That's because we needed to take a long exposure in order to bring out the detail of the stars, which appear as little trails because during the photographic exposure, the Earth is actually turned a little bit. As a consequence, both the moon and indeed the streetlights of Penzance are horribly overexposed. So the photographs taken by the astronauts, I would allege, don't show any stars for the very simple reason that they're short exposure photos and the background light from the moon's surface itself is illuminating the scene far more greatly than the stars themselves. Although curiously, if you actually go and have a look at the NASA archives where many of these images are stored, what you find is that downloading the images, increasing the contrast and inverting the colours, maybe it's a little hard to see, but does reveal some little black dots in the photograph. Now, for all I know, those could just be defects in the photographic film, but they might be stars. I guess my main point is that these are simple experiments and investigations that people can carry out for themselves. But I think it's an interesting topic, the absence of stars, to really get you thinking about how photographs work and how the physics of photography influences this question. Now, time is short, so as I say, there's many of these topics that I greatly encourage you to go away and have a look at for yourself, but I'm going to jump ahead a little bit now, and I'm going to talk to you about dust problems. But I want to talk about this one because there's some very good science here and some quite fun experiments that we enjoyed putting together. And many of the schools with whom I've worked in the UK, they've done some wonderful project work on this topic for themselves. So basically, let's have a listen to what the TV show says first.
In the end, there's one set of evidence that is irrefutable, and that is that there are footprints, boot prints, still on the lunar surface.
But conspiracy theorists say that the footprints themselves are suspicious.
The surface appears to be very fine-grained as you get close to it. It's almost like a powder.
To have a powerful rocket engine blast the surface of the moon, blasting away all of the dust, and then find footprints surrounding the lunar lander, that to me would be an impossibility.
Photo after photo reveals that the lunar surface surrounding the LEM is covered with footprints.
So Bill Kaysing is having us believe that the powerful rocket engine on Apollo 11 and the later missions would have blown away so much dust that you couldn't have any footprints, and moreover, that you should have had a major blast crater underneath the lunar module. Well, to try and address that one, let's first of all have a brief look at the final descent of Apollo 11. Long before the time of many people in the audience, I was only about 18 months old myself, but this is where Neil Armstrong and Buzz Aldrin are piloting the Eagle Apollo 11 lunar module down onto the moon's surface. And the main thing to note here is that they're not really descending very rapidly. They're going mainly sideways, in fact. And the reason for that was very important. There was real concern that they might wind up landing on a sizable boulder which would tip over the lunar module and end the mission very fast. So they were in the business of trying to slow their descent as best they could in order to ensure a safe landing. So this notion of a powerful rocket engine decelerating them very quickly, as was alleged by Bill Kaysing, doesn't really seem to add up. And again, don't take my word for it. If you think about what the effect of a rocket engine would be, if it was indeed blasting away at the moon's surface, then the conspiracy theorists would claim that that would make this large crater as well as blowing away all of the dust around. But here's what an engineer from NASA has to say about it.
The fact that there's no blast crater under the LEM is one of the most conclusive pieces of evidence that I find supporting the hoax.
In fact, no sign of a blast crater is visible for any of the 6 lunar landings. But LEM specialist Paul Fiel says he can explain why the lunar module left no crater when landing on the moon.
The amount of thrust that you need coming out of the bottom of the descent engine is about 1,500, 2,000 pounds of thrust. And all that does is just push dust away. There's no burning or anything like that. Yep.
So he's saying that there's no burning or anything like that. The crucial thing here is that Paul Field, one of the NASA engineers, actually quotes some numbers. Science is all about being quantitative. It's about measuring things. It's about working things out as best you can, rather than just making wild guesses or rather speculative answers. So we thought we'd explore that a little bit, and in setting up an experiment, again, it was a bit difficult to replicate the exact conditions you would have had on the moon, but what we wanted to do was to explore just what the effect of the engine of the lunar module would have been on the dust on the moon's surface. First of all, notice that there are some photos that indicate a small crater, a small amount of dust does indeed appear to have been disturbed immediately below the engine. We'll come back to that point in a moment. But first of all, let me show you our little experiment. We had great fun doing this. We got to build our own lunar landscape first of all, and then populate it with some dust in the form of some flour. And then along comes our lunar module in a moment, and what we're doing is blowing some compressed air through the lunar module, aiming it directly downwards to try and simulate the effect of the engine disturbing the dust immediately below the lunar module, but not anywhere else. And then in a few seconds you'll see our brave astronaut coming along, and sure enough, there's still plenty of dust around for him to make footprints in our lunar surface. Now, I know it's not exactly very rigorous science, but nonetheless, what we're trying to explore here is how the absence of an atmosphere in the moon would change things compared with how dust would behave on Earth. And to look further at that, we'll not just think about the effect of the lunar module landing, but also the lunar rover, the moon buggy, which the Apollo astronauts used a bit later on. And before we get to the moon buggy, let's have a watch of a brief video clip of a rally car racing down here on Earth. So what we see going on there is that as the rally car races along the dusty road, the wheels are turning very fast. Those wheels are disturbing dust on the road, which in turn can then transfer some of the energy of the car moving along to more dust. That creates this billowing cloud of dust, but there's a very crucial element that makes that possible, which is the air molecules in between the dust particles. Now, this is a phenomenon which you can study in a variety of different ways. No less a person than Albert Einstein actually did some of the theory related to this about 100 years ago. And the phenomenon is called Brownian motion, the random motion of the dust particles which bump into the air molecules, which in turn bump into more dust particles. Before you know it, you've got a billowing cloud of dust. And again, I could have showed you similar footage of, say, a helicopter landing, or indeed a spacecraft taking off from the Earth. You get a billowing cloud of gas and dust produced by such a dramatic event. What about on the moon? Well, let's have a look at what the lunar rover does on the moon. First of all, notice there's no sound this time, but look carefully at what the dust is doing. The dust is not producing this large billowing cloud. Instead, it is indeed being thrown up by the wheels, but it spreads out a little, but not nearly so much. And in fact, what the dust does is forms a particular form of mathematical curve called a parabola. Now, that parabola is the shape of curve that, say, if I take a coin and I throw it over here, the coin will go up and then it will go down. It will follow a curving arc. On Earth, dust doesn't do that because dust floats because of air resistance again. On the moon, dust will follow a curved path just like a coin or a rock or something much heavier. In fact, it won't follow exactly the same path as it would on Earth because the gravity is lower. But crucially, if you think of the lunar module landing or the lunar rover chugging along the moon's surface, in both cases, you don't have the air to help create the billowing cloud of dust that we saw with the rally car. So the presence of the footprints which the Apollo astronauts made would seem quite compatible with the absence of an atmosphere on the moon. Moreover, as I said, you can measure the curving arc of the dust thrown up by the lunar module, and based on the curvature, you can work out what the gravity is. That's a really quite challenging little experiment, but something you might want to have a go at for yourself. There's video capture software, which I guess most schools would have access to, which would allow you to analyse the motion of the dust on the footage. We've had a look at that, and sure enough, it gives you an answer consistent with the lower gravity of the moon. And I'll come back in the final few minutes to this idea about the low gravity on the moon as well. So the last of the main topics I want to briefly look at is, I'm sorry I don't have time to go through all 10, but as I said, the resources are all there on the web, as we'll see at the end, and I encourage you to go away and have a think about these for yourself. But let's just have a brief look at radiation before we wrap up.
Any human being traveling through the Van Allen belt would have been rendered either extremely ill or actually killed by the radiation within a short time thereafter.
Other than the Apollo missions, no other manned space flight has attempted to pass through this deadly radiation.
What we have to bear in mind is that the radiation damage, both to life and to buildings and so on, caused by those explosions was rather different from the main radiation threat which the Apollo astronauts would have faced. The main radiation threat which the Apollo astronauts had to deal with was charged particles coming from the sun, what we call the solar wind. Now these are trapped by the radiation belts around the Earth, and that's good news for us because it stops them reaching the ground and harming us. But in fact, those charged particles are basically protons. They are the nuclei of hydrogen atoms because the sun is mainly made of hydrogen. Now radiation comes in a variety of forms. You've got protons, like the solar wind. You've got the nuclei of helium atoms, which are known as alpha particles. And then you also have another form of radiation called beta particles, which are like the positive counterpart of the electron, a positron. In addition, you have ionizing radiation, which is in the form of light, but light of very high energies, ultraviolet, X-rays, and gamma rays. Gamma rays in particular are extremely harmful. And moreover, if you wanted to shield yourself from gamma rays, well, you really need several inches of concrete in order to do it. Even X-rays, you need a substantial thickness of lead. That's why if you go to get an X-ray at the hospital, the radiologist will stand behind a lead screen to shield his or herself from the X-ray exposure. But if you want to shield yourself from protons, really all you need is a few centimeters of wood. Now, I do concede that building the Apollo lunar module out of wood would not have been NASA's smartest move, but a few millimeters of aluminium will do the job just as well. And again, a demonstration I normally take to schools in the UK is a source of, well, in fact, it's usually alpha particle radiation, but protons are broadly similar, and a Geiger counter takes some aluminium foil and demonstrates that the foil will shut off most of the signal. But the key message is that radiation comes in these different forms. The sun does produce gamma rays, but in most copious amounts at times of a major solar flare event. Unfortunately, there weren't any such major solar flares during the Apollo missions. If there had been, then the astronauts could indeed have been in big trouble. The proton threat from the solar wind is a much more manageable threat. The aluminium shell of the spacecraft was more than adequate. Moreover, they passed through these Van Allen belts fairly quickly in just a few hours on the way to the moon. So ironically, the claim made by the program that no one has been beyond the Van Allen belt since, actually, there's a much greater threat if you're on board the International Space Station. I mean, it's still perfectly reasonable. There's no evidence that the astronauts on board the space station have suffered any long-term harm. But because they are continually being exposed day after day to small amounts of ionizing radiation as they pass through the Van Allen belts, then it's a threat that has to be taken seriously. The way the body reacts to radiation exposure is that if it's not too energetic, not too ionizing, and doesn't last for long, then the body will recover just fine. So that really brings me to a few concluding remarks. Again, there's plenty more to discuss in the other topics I've not had time to cover, but I encourage you to go away and have a look at them for yourself. So let me just wrap up by a few remarks about the counter-arguments that people have often come along with. They've sometimes said, well, couldn't we use the Hubble Space Telescope to look at the moon? Wouldn't that show us images of the lunar landing sites, and then that would settle it one way or another? The Hubble telescope is probably still pound for pound the best telescope we have up there in space. There are bigger telescopes in the ground, but because they've got to look through the atmosphere, they don't give us as sharp a view of distant objects in the universe. The trouble is, though, the Hubble telescope's just a few hundred kilometres above the Earth. The moon is 400,000 kilometres in the other direction. So even though we've grown accustomed over the years to seeing images like this one, that's of Sydney Harbour, or this is Frankfurt Airport, the kind of images that you see in like Google Earth, for example, many of them taken by aircraft, but some taken by satellites. If you use the Hubble telescope to look at the moon, because it's so much further away in the other direction, even the Hubble telescope doesn't have sufficient resolution to reveal the Apollo landing sites. This is an image of the moon taken by Hubble, and it shows a large crater called Copernicus, which is about 100 kilometres across. So each pixel of the image is still about 70 metres across, way bigger than the Apollo lunar landing site. However, in the last few years, there's been a satellite actually orbiting the moon itself called the Lunar Reconnaissance Orbiter. And it sent back some images like this one, which NASA released in July of 2009 to mark the 40th anniversary of the first lunar landings. So according to NASA, that is Apollo 11. According to NASA, for Apollo 14, you get an even better view. You can see the lunar module, footpaths of the astronauts, some of the instruments left behind. Now, of course, again, the conspiracy theorists will probably just say that these are faked as well, but I'm prepared to give NASA the credit that what we are actually seeing is the lunar landing sites. So here's another couple of ways that I would regard as having proof that the moon landings really happened. Lots of video footage was tracked by a network of satellite dishes, radio telescopes on the Earth's surface. There was a movie a few years ago called The Dish about one such radio telescope in Australia. Okay, the movie fantasised the story a little bit, but I know some of the astronomers who worked there in Australia at the time, and as far as I know, their story checks out. They say that basically they were getting signals from the moon. They can't say that there were really astronauts up there, but there was something up there beaming those signals back. And then there's all the moon rocks that were brought back, which my geology colleagues tell me, if you look at them under a microscope, they show the unique signatures of billions of years of exposure to an airless environment with lower gravity, no water, but crucially also no air, to erode away the surface of the rock in a smooth manner, the way that it happens on Earth. Then there's a variety of experiments that were carried out to measure the distance to the moon by bouncing a laser beam off the moon's surface. And in fact, one such experiment featured in my very first image, because the instrument that Buzz Aldrin is carrying is this little thing here left behind. It's a laser reflector to ensure that the laser beam bounces straight back. Without that being there, the beam would be too diffuse by the time it reflects off the moon for you to measure anything. Now, there's hundreds of such experiments have been carried out, including by scientists in China. Are they in the conspiracy as well? Again, a question I put to the conspiracy theorists. And then finally, back to this notion of dust and floating dust on the moon's surface, or in particular the fact that dust doesn't float on the moon. Let me just wrap things up by showing you a brief video clip taken by Apollo 15 astronaut David Scott, and I'll let him explain what's going on.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
So not only do you see the hammer and feather fall at the same time, the same rate, there's no air resistance to make the feather float, but they do take longer to hit the ground than they would on Earth, and if you measure the acceleration, you get 1/6 that of Earth gravity. Now, we had a student work with us on this to do some analysis of that video footage, and maybe he was just trying to wind us up, but he said, what would happen if he did the measurements and he discovered that you got 10 meters per second, which is the gravity of the Earth? So we teased him back and said that that's the point where the men in the dark suits and the dark glasses would come through the door. I'm pleased to say that that was not what he measured, and it's not what's about to happen to all of you today. But to emphasize the fact that there is a lot of stuff out there, and it's hard to know what to believe and what not to believe, let me end with this short video clip, which will give you food for thought as you take away this question of, did we really land on the moon?
That's one small step for man, one giant leap. So, I guess you want to do it again. Okay.
I'm fairly sure that one's a fake though. So let me leave you with the web address where you can download all of this. I've also got that as a tiny URL, which is a bit easier to digest. And indeed, we have as a dedicated email address if anyone's got any questions about moon landing conspiracy theories, or if you come across some evidence that you think maybe backs them up and you want to see what I think, then by all means get in touch. Thanks very much, and I hope you've enjoyed my talk.